This is our last video for this unit, and in it we're going to talk about nuclear stability and nuclear reactions. But first, before we begin with that, we're going to talk about relativity. Because there are some consequences to what Einstein said about it, relativity, that are going to affect what we do with nuclear stability and nuclear reactions. So, nope. Einstein's big idea with his theory of relativity, or at least the thing that spurred him on to think deeply about this and give us some very interesting results, is that the speed of light is a constant for all observers. Now, this may not seem earth-shattering, and this is actually something that Maxwell and Faraday said. Einstein just took it to be true, and he was the first one that said it. So to do this, I'm going to use an example that is not something moving at the speed of light, just to kind of give you an idea of the weird changes that happen here. So normal traditional mechanics, imagine that we have a train or a platform that we're riding on. That platform is going 2 meters per second, and we're throwing baseballs, not at 10 meters per second, sorry, at 3 meters per second. And we're going to say that this is 6 meters long. We're standing at the back. Okay? And then we're going to have an observer watching. So what you see is going to be different than what the observer sees. The velocity of the ball to you, okay, is 3 meters per second. The velocity of the ball to the observer is 5 meters per second. Okay. You see yourself throwing the ball at 3 meters per second relative to the top of the platform that you're riding on. The observer sees the ball's velocity and the platform's velocity added together. This is just normal relative velocity stuff that we've done before. You would also say that the time it takes to get across the top of the platform is 2 seconds. And the observer would say that the time it takes to get across the platform is 2 seconds. And so right here in this classical mechanics situation, we're saying that time is constant. Okay, that's a normal thing. These are the things that we expect to see. These velocities add based on where we are. Okay, time is constant and velocity is relative. The velocity changes based on where you're standing and what you're observing. So, in a relativistic example, we're going really fast. This is according to Einstein's relativity, but I don't want to write out all those numbers. So what we're going to do is say, okay, we're going to have the same train. This is a little bit of an analogy. The train is still 6 meters across. You're still up here throwing the ball at 3 meters per second. And the train is still moving at 2 meters per second. And we have the same observer. But in this case, okay, we're going to qualify things, and we're imagining imagine the ball as light. And so that speed of 3 meters per second is really a speed of 3 times 10 to the 8th meters per second. And we'll write that somewhere else where it's a little bit easier to see. So, that's not bad. So, we have what you see, and we have what the observer sees. Outside, standing still. What you're going to see is the velocity of the ball moves at 3 meters per second, or the velocity of light is the same, 3 times 10 to the 8th, and the observer sees the velocity of the ball as equal to 3 meters per second. He's not seeing the velocity of the ball change at all. In fact, the observer is seeing the ball moving at 3 meters per second. The platform or the train moving at 2 meters per second. So the ball is only going 1 meter per second faster than the train, even though you think you see the ball is going 3 meters per second faster than the train. That's the first sort of little hitch. The next thing is the time. Time here is very strange. You see it taking 2 seconds to go across the top of this thing, still 2 seconds. But the observer now sees that same action, and he clocks the whole thing at 6 seconds. Okay? Because for him, the ball is only going 1 meter per second faster than the train. Every second, the train to him moves 2 meters, and the ball moves 3 meters. So it's going to take 6 seconds for the ball to pass across the train immediately. And so, what we see here, what Einstein says is that time is relative. In fact, a couple of things happen as we start going the speed of light. So as an object reaches the speed of light, one thing that we see 3 big things. One is that we observe time slowing down. And that's kind of what we saw with the ball. The second thing that we observe as we watch an object get closer to the speed of light is that lengths contract or get smaller. And if you want to talk about that one, we can talk about that more in class. But in the same way that time adjusted to make sure that the speed of light was still 3 times 10 to the 8th, length will do the same thing. And the one that's we're gonna spend most of our time with, okay, lengths get smaller, is that mass approaches infinity. And so there are a couple of consequences to this. That's what we're going to talk about on the next page. But mass approaching infinity is the one consequence of Einstein's relativity that we're going with. So, our idea here is one of infinite mass. A little chart that we have for that. Put mass over here. Speed here. And this little border I'm going to call c, or the speed of light. And so the mass of my object is going to stay pretty much the same until we start getting close to the speed of light. And what Einstein said is as an object approaches 3 times 10 to the 8th meters per second in velocity, the mass becomes infinite. And one of the immediate consequences of this is that no object can move at the speed of light because it would take an infinite amount of work to do so. Now, we really just kind of need to know those two statements, but the big thing that this gives us, the big thing that Einstein got out of this, was his rather famous equation, E equals mc squared, or energy is mass times the speed of light squared, where c is 3 times 10 to the 8th meters per second. And so if we ever use that equation, we're going to square it. And our first proofs for this came from our proofs for this came from the first proofs, nuclear reactions.
Junior class powder puff.
So, in a nuclear reaction, well, we have two main ones, fission and fusion. What happens is elements combine or elements split, and a tiny amount of mass is lost. So, what we're going to say is in both fission and fusion, elements combine or split and a tiny amount of mass is lost. This mass becomes energy. Sorry, this mass, spelled that wrong, becomes energy. And it follows this whole E equals mc squared thing. So one thing to keep in mind in these reactions the total number of neutrons and protons is constant. So the total number of neutrons and protons is constant. So when we lose that mass, it's not that we have a neutron or proton disappearing. What we actually see is the mass of the neutrons and protons themselves changes. Neutrons and protons have different mass in different elements. Didn't mean to cross that out. Neutrons and protons have different mass in different elements. So we have a nice little handy-dandy chart that kind of helps us out with that. And in our chart, we got this. And again, this is a rough chart, so well, not exact drawings, but we have the atomic number down here. So what atom we're talking about. And then we have nucleon mass, or the mass of the proton and the neutron. So what this says is that, and then we have this where it kind of levels off here. Stable, and it's stable close to iron and nickel. That's sort of our stable point. What it says is as we move from up here, hydrogen, to helium, to heavier elements, the mass of the neutron and proton gets smaller. So here we're going to see a lot of fusion. I don't want to say this. So in that we have two light elements come together to form a heavy element. When that happens, we're moving down this thing. That means when two light things come together to form a heavy thing, we lose mass. My neutrons and my protons get lighter, and that loss in mass goes into the E equals mc squared, and we get a huge amount of energy out. So as we go from lighter elements to heavier elements, the neutrons and protons lose mass. And then over here on this side is where we get fission. Here we have a heavy element breaking into lighter elements. And when that happens, when we start here and we break into two lighter elements, okay, again, the neutrons and protons, we're moving back down. Those neutrons and protons have lighter mass. That change in mass is my energy released. And then it happens to be that our stable point is around iron and nickel. So all of these fusion and fission reactions happen to get greater stability. We see nuclear reactions when there is not a lot of stability. So for fusion takes place under conditions of high energy, high pressure. So when you put a lot of hydrogen under high pressure with a lot of heat, it's more stable as helium. So it changes into helium, it releases that E equals mc squared energy. That's what we see happening. With fission, we take something and we make it unstable. So like unstable uranium, we shoot a neutron at it. We shoot a neutron at the unstable uranium, it makes it unstable, and then it breaks apart into two different elements that are lighter. It's going from an unstable form to a more stable form. Those are sort of natural fissions. Same thing with radioactive decay. Now that's different than the fusion fission spectrum. Completely different set of rules that govern how that works, but you have an unstable nucleus decaying into a more stable nucleus. All nuclear reactions are about stability.